Welcome to the Explainer. So let's just dive right into it. We live in a world where we are generating absolute mountains of digital data every single day. I mean, every click, every purchase, every single song we stream, it's all data. But here is the massive core problem. How does artificial intelligence actually make sense of all this raw information when there are literally no instructions or labels attached to it? How does it actually find the signal in all that noise? Which brings us to our first concept, the unsorted Lego box, and discovering unsupervised learning. To make this super easy to wrap our heads around, let's start with a really physical analogy. Just imagine someone handing you this massive box of mixed, completely unsorted Lego bricks. You've never seen these specific pieces before, there is no instruction manual, and no one is telling you what you're supposed to build. Left completely to your own devices, what would you do? Well, naturally, you'd just start finding patterns. You'd probably start grouping them by color, putting all the red ones in one pile, or maybe by size and shape, stacking the long bricks over here and the tiny squares over there. And honestly, that is exactly how unsupervised learning works in the AI world. The computer does exactly what you just did with those Legos. It gets raw data with absolutely zero labels and zero correct answers. This is a total contrast to supervised learning, where you hold the AI's hand and tell it exactly what to look for. In unsupervised learning, the AI's primary goal is pure discovery. It's actively hunting for hidden trends, structures, and behaviors that even the smartest human managers didn't know existed. So let's pivot and look at finding hidden business patterns with the three key AI detectives. Taking this from the toy box straight into the boardroom, within unsupervised learning, we have what we can call the big three methods. First up, we have clustering, which is all about grouping similar data points together based on shared traits. Second is association, which discovers these wild hidden links and rules between completely different items. And third is anomaly detection, which basically acts as an automatic red flag system for things that just do not look right. Let's zoom in on that first one, clustering. Specifically, we're talking about the famous k-means algorithm. This mathematically groups raw data into completely organic segments. It starts with all this raw, unlabeled data, and then initializes a specific number of groups, which the pros call k-centroids. From there, the algorithm iteratively assigns data points to these clusters, minimizing the distance between them until, boom, clear, distinct groups naturally just emerge right out of the chaos. To put that into perspective, think about how Starbucks uses this in practice. Instead of some human marketer just guessing what customers might want, the k-means algorithm processes millions of users' order times, drink types, and purchase frequencies. It automatically clusters them into these highly organic groups. So you might get a cluster of morning coffee addicts who show up at 7 a.m. on the dot every day, or weekend pastry buyers who literally only come in on Saturdays. The business can then deploy hyper-targeted push notifications, meaning they only tempt that weekend group with a double chocolate croissant, completely maximizing their marketing return on investment. It's brilliant. Moving on to our second method, association. Here, we're looking at the a priori rule, which digs into transaction histories to see what naturally belongs together in the mind of the consumer. If you have ever shopped on Amazon, you've definitely seen this in action. The second you put a smartphone in your cart, the algorithm instantly powers up that frequently bought together section, tossing out a specific phone case and a screen protector. And it doesn't do this because of basic demographics. It does it because it found deep, hidden links buried in millions of past shopping baskets. And to protect all of those millions of digital transactions, we rely on our third method, anomaly detection. Instead of a human manually combing through endless, mind-numbing server logs, this algorithm instantly spots things that are just out of the ordinary. In the finance world, it acts like a digital shield. It's sifting through millions of records to instantly block fraudulent credit card charges and spot massive corporate billing errors way before the money ever leaves the bank. Talk about a game changer. Now, let's step out of the corporate backend. We're moving on to powering your digital experiences and how AI curates your world. Let's look at your personal day-to-day digital life. We are talking about recommendation algorithms. These AI engines filter absolutely vast amounts of content to predict exactly what you want to watch, buy, or listen to next. They rely on explicit feedback, like your 5-star ratings, and implicit feedback, like tracking exactly how long you spend staring at a post. But to actually make those predictions, they use two entirely different methods, collaborative filtering and content-based filtering. To build your highly personalized feeds, these engines take two completely distinct approaches. Collaborative filtering is entirely behavior-based. It's like Netflix noticing that your specific taste cluster of users all binge-watched the sci-fi show Arcane. And since those exact same users also loved Stranger Things, it recommends Stranger Things to you. The logic is simply, hey, people just like you also liked this. Content-based filtering, on the other hand, is completely different. It totally ignores what other users are doing and looks directly at the specific DNA of the item itself. It's like Spotify analyzing the actual acoustic characteristics of a song, the tempo, the key, the instrumental density, and finding a perfect sonic match by some unknown indie band you've never even heard of. It recommends it simply because the audio DNA perfectly matches the vibe you already like. But AI goes way beyond digital content. Let's get into solving complex real-world puzzles and the search for the best possible solution. See, AI has to operate within the messy, extremely physical world using what we call optimization algorithms. These are heavy-duty mathematical tools designed to find the absolute best possible solution from a massive pool of alternatives. Think about supply chain logistics. A delivery truck has dozens of stops across a massive city. The math involved here is frankly overwhelming for a human, but these algorithms can search trillions of combinations to find the shortest, most cost-effective path. And they do it while navigating strict, real-world physical constraints, like live traffic jams, extremely tight delivery windows, and fluctuating fuel costs. And hey, it's not just for delivery trucks. Optimization is incredibly critical for human resources, too. Take massive seasonal spikes in business demand, like the holidays. Companies use these workforce scheduling algorithms to dynamically match employees to specific shifts. It perfectly balances worker preferences, required skill sets, and hardcore business needs to ensure the whole operation runs fairly and super efficiently. Which brings us to our final section, the ultimate AI trade-off and choosing the right detective for the job. So, with all these unbelievably powerful tools sitting on the table, how does a business executive actually decide which one to use? Well, no single algorithm is perfect for every single problem. Organizations have to rigorously evaluate them across 4 crucial pillars. First up is accuracy. Basically, how often does it actually make the correct prediction? Second is interpretability. How easily can a human actually understand and explain the algorithm's internal logic? Third is complexity. How technically difficult is it to build and maintain the thing? And fourth is scalability. Can it handle massive, constantly increasing amounts of data without totally crashing? This creates the ultimate AI trade-off. Just picture a seesaw. On one side, you have accuracy and complexity. On the other side, you have interpretability. There is a really strict inverse relationship here. As an algorithm becomes highly advanced and incredibly accurate, say a deep neural network or a support vector machine, it unfortunately becomes a black box. It becomes significantly harder and sometimes literally impossible to explain its inner logic to human beings. Let's look at a real-world scenario to make this concrete. Imagine a bank that's trying to predict whether customers will default on their loans. They basically have 2 options. They could use a random forest algorithm, which acts like a massive, complex committee of many individual decision trees. It gives you phenomenal, high predictive accuracy, but it's virtually impossible to explain the wildly complex paths it took to reach that decision. The alternative is using a single, simple decision tree. Now, it might be slightly less accurate mathematically, but its logic is entirely transparent and incredibly easy to trace step by step, which, by the way, is exactly what strict banking regulators demand. Which brings us to the absolute core dilemma of modern AI, and the question I really want to leave you with today. If you were that bank executive, how would you balance the need for the absolute highest mathematical accuracy against the fundamental human need for transparent, explainable decisions? It's a huge reminder that the best AI isn't always the most computationally advanced one. It's simply the one that aligns best with your actual real-world business goals. Thanks so much for joining me on this explainer. Keep asking those big questions, keep looking for those hidden patterns, and I will catch you all next time.